Hi, so this is lecture 7 of our video lectures. We're going to be discussing a lot about operators today, what they are and how we can represent them. Before we get into that details of operators though, I want to recap the postulates of quantum mechanics. These are mentioned at the end of chapter 1 in your textbook, and there's 6 of them. They going through them in order. One is the state of a quantum mechanical system, including all the information you can know about it, is represented mathematically by a normalized ket. A physical observable is represented mathematically by an operator A that acts on these kets. The only possible result of a measurement of an observable is one of the eigenvalues A sub n of the corresponding operator A. The probability of obtaining the eigenvalue an in a measurement of on a system that is in the state psi in this ket is given by the projection onto that an squared. After the measurement, the system is then in a new state that corresponds to that eigenvalue the result that was the result of that measurement. The way the book words this sounds a lot more complicated, but the system is in a new state that is the normalized projection of the original system ket onto the ket corresponding to the result of the measurement. And then finally, the evolution of a quantum system is determined by the Hamiltonian or total energy operator H of t through the Schrodinger equation. So these are the 6 postulates of quantum mechanics. We're working through them, and we're slowly going to get through it and learn more details about what all these are. In the first chapter, we kind of discussed, or at least alluded to, these 3. The first one was one of the first things we said is that we can represent quantum mechanical states with using a ket. Number 3, the fact that measurements are quantized, we discussed, but it's essentially this thing. If you have some observable, some thing you can measure, we'll call the observable A, you only can get certain distinct values that we call eigenvalues of that operator. And the last one we did spend some time discussing is the probability of obtaining an eigenvalue in a measurement of the system A is given by this probability equation. So we've seen some of these before. The kind of goal of chapter 2 is to discuss more formally, build on our mathematical description and toolkit that we use in quantum mechanics so that we can better understand 1 through 5 of these. By the end of chapter 2, we should have a good grasp of these first 5 postulates, and then chapter 3, we get into the evolution, the time evolution of these quantum systems with the Schrodinger equation. The first thing we need to capture all these is a word that's thrown around a few times in here is operators. So operators are mathematical objects that they're called operators because they operate on these quantum mechanical kets and transform the ket into another ket. So we have our generalized ket psi here. The operator A acts on that ket, and the result is a different ket. It's in the same Hilbert space, but it basically just converts one ket into another ket. For a given operator, there are certain kets that when the operator acts on them, it only changes that ket by some multiplicative factor, right? So if you have some operator on one of these kets psi, if that operation amounts to not really changing the ket, but just multiplying it by some scalar, that's what we call an eigenvalue. So for a certain operator, there will be a number of kets that we call eigenvectors or eigenkets that when the operator acts on those kets, the result is the same ket just multiplied by a scalar that we call the eigenvalue. And this is important. Postulate 2 and 3, postulate 2 being that the observables are represented by operators, and postulate 3 that the measurement of an observable results in one of the eigenvalues. You can immediately see why we want to have a strong understanding of this picture. These A's give us the results of our measurements. They're the quantized things that we can measure through some measurement that's represented by this operator. So what did this look like for our spin 1/2 system in the Stern Gerlach? Well, if you remember, we had the SZ measurement operating on a spin up state, gave us the H bar over 2 spin up state. That is an eigenvalue equation. We have some measurement operator acting on a eigenket, and we know it's an eigenket because the result of that operation gave us our scalar value, the result of that measurement, and the same eigenket we had before, right? We also had the SZ measurement on our spin down state, gave us the negative H bar over 2 operated on the same thing. So those are two eigenvalue equations uh, for our spin 1/2 system in our SZ measurement, our Z component of the spin angular momentum. Now, for those of you who probably remember from linear algebra and mathematical physics, eigenvalue and eigenvectors are words we apply to matrix algebra. You know, these are common terms in that type of math, and it's obvious. Hopefully, everyone can see that this is going to map with why we're using the matrix representation we had before. If you remember, our spin up state plus in the matrix representation was just the unit vector 1, 0, and the spin down state was the unit vector 0 and 1. Operators like SZ are actually just going to be in the matrix representation are going to be represented by matrices, right? And in this two-dimensional Hilbert space, this two-dimensional system we're describing, the spin 1/2 system, they're just 2 by 2 matrices. So we can write this, I'm going to keep using the book's notation, this SZ operator represented as a matrix. Now, again, just like when we first discussed these spin up and spin down basis vectors as column vectors, we needed to be sure which basis we're using to describe that, and we're using the Z representation uh, where our basis vectors are the plus and the minus. Um, so how does these eigenvalue equations here, how do they look in our matrix representation? Well, the SZ spin up equal to H bar over 2 spin up state, that maps to A, B, C, D. Our SC matrix times 1, 0 is equal to H bar over 2, 1, 0. And likewise, our SZ minus is equal to negative H bar over 2 minus. That maps to, again, A, B, C, D, that 2 by 2 matrix, 0, 1 equal to negative H bar over 2, 0, 1. Now, uh, this is actually enough information that we can sort of solve for what our matrix representation is. You know, both of these two equations give us or can be used to solve this A, B, C, and D. In the first equation here, we have A is equal to H bar over 2. Just do the matrix algebra. You get A is equal to H bar over 2. This ends up being A, so we'll write out the full result of that. H bar over 2 over 0. That is what our AC looks like that we get from here. If you just take the 1, 0, multiply it by that, and then by that, you get that. The second equation down here gives us similarly, we get BD is equal to 0, negative H bar over 2, right? So what this tells us is that our SZ operator can be represented by H bar over 2, 0, 0, negative H bar over 2. Or written another way, just H bar over 2, 1, 0, 0, negative 1. And we have our matrix representation of our SZ operator. Now, there are a few things worth noting about this SZ operator. All right, so let's just give us some fresh space over here and rewrite it. SZ represented as h bar over 2, 0, 0, negative h bar over 2. The first is this is diagonal, right? We have a diagonal matrix, and that turns out to be true for any operator written in its own representation. So if you remember, we are using that Z representation where we're writing these matrix representations based on the Z eigenbasis. So the fact that these matrices are written such that the order of the eigenvectors we're describing them in are plus and minus. These are the eigenvectors of the SC operator. That tells us we're going to get a it's going to be a diagonal matrix. All operators are diagonal when written in their own bases, just like those eigenvectors are just unit vectors in their own bases. So those two properties are always true. If you're describing a system in a given eigenbasis, those eigenvectors are just going to be unit vectors, and the operator is going to be diagonal. Another thing that's worth pointing out here that really leads to some nice compact notations here is we can rewrite that this SC matrix um, as plus SZ plus, and then this would be plus SZ minus and minus SZ plus minus SZ minus. This might not be obvious to everyone um, looking at this for the first time, but let's just look at one of these elements. If I take that SZ operator and I sort of sandwich it between the two spin up eigenvectors, well, I know that this part, SZ operating on the spin up state, it just gives me h bar over 2 times that spin up state. And that this is a scalar, so I can take it out and just move it around. It commutes to there, and then I get plus and plus, which I know because this is an orthonormal basis, that equals 1. So this is equal to h bar over 2. And I can do the same thing with all of these, right? And so you can rewrite your operators in this nice compact notation where I can write a general matrix. So if I have some operator A and I want to write that as a matrix, I can just write it as A11, A12, sort of how I would generally write A1n, A21, dot, 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 AN1. This entire matrix, which, could have any dimension. It doesn't have to be a simple 2 by 2 matrix, depending on the system we're describing. I can capture that whole matrix in this nice notation where those matrix elements are just the ith bra and the jth ket sandwiching that operator, where this I is the ith eigen bra of our representation, and this is the jth eigenvector, eigenket, we'll call it. And you can get all of those, and this gets especially nice for in terms of a compact notation if we actually want to look at what these operators will do, right? So we have A operating on some general ket. Now we can recall that because of our eigenbases, it forms a basis and is complete, we can write this ket here as a linear combination of these coefficients times the eigenkets. We can just write it as a linear combination of our basis states here. So this in the matrix representation, this whole equation, the operator acting on our ket and converting it to a new ket, can be written in this, very tedious to write the whole thing notation, I at 1n. Then this phi1, phi2, phi n, where these are just these coefficients from our expansion. And this is going to equal another column vector that can be expanded in the same way, but it's just going to have different coefficients. This whole representation can be very much simplified, right? This equation boils down to that a11 phi 1 plus a12 phi 2 dot 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 a1n phi n. And this is second row is going to be a21 phi 1 plus dot 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 a2n phi n. This goes all the way down to an1 phi 1 plus an2 phi 2 dot 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 n phi n. If we do the multiplication of these two, that's what we get, and we know this is going to be equal to b1, b2, bn. So this can all compactly be written in terms of bi is just going to be equal to the sum over j ai j phi j, where phi j is just the coefficients of the initial ket that we were in before the operator operated on us, and aij is the matrix elements of that operator. So that's the gist of what operators are, how we represent them in our matrix notation. Next video, we're going to actually look at some specific operators and sort of flip the question around. We've kind of approached this from we have an eigenvalue, we have the eigenvectors and the eigenvalues for our SZ operator. We're going to kind of flip that around and say, okay, what operators do we have in the matrix notation? How can we determine what the eigenvectors and eigenvalues are? Because that's more likely to be the case that we'll see. We have some measurement operator, and we want to know what the results of those measurements would be, i.e., what are their eigenvalues, and what states did the system end up in? What are the eigenvectors of that operator? So the next video, we'll start looking at that.